Welcome everyone again to second year physical chemistry, and today we are going to go and learn about the Gibbs free energy and its origins. What will be covered and why? Well, we will cover the Gibbs free energy. And why? The Gibbs free energy describes all chemical systems. I want to make sure that you understand its origin and how to read it. So, just to put this presentation in context, we have started off with the laws of thermodynamics. We reviewed it, and then we applied some maths to the laws of thermodynamics and got some interesting equations out. What we're doing now is we're going to go, we're going to go from the laws of thermodynamics and we're going to start rewriting it for chemical systems. What will you need? Again, you will need to remember calculus. And again, it will have to be differentiation, and we will use the product rule again. We will also be dealing with partial differentials. And for the topic, you can consult Atkinson's Physical Chemistry. The sections to look at is the second law and third laws, concentrating on the system. Also look up in the index Gibbs free energy. And the second and third laws, combining the first and second laws. So this will help you understand the content of this lecture. The Gibbs free energy. I have to start off and make an emphatic statement to say that the laws of thermodynamics, as we've reviewed them, are complete. They describe everything you want them to describe. But there is a problem. So let's take a look. Here's our thermodynamic identity for a reversible process. You should now be loving this equation. But we note, and I note that it's a complex equation. So the first thing I want to ask you is, what are the variables of the system? In other words, what are the parameters that I will need to change in order to change the internal energy? So I want you to pause the video and write down what you think the answer is. What are the variables of the system? Alright, I hope you've paused and give it a go. First thing to do is to write this in terms of partial differentials. So, the internal energy is equal to changes in the volume multiplied by this partial differential, which is the partial differential of the internal energy with respect to volume, if you keep the entropy S and the quantities of material Ni constant. And you can do it for each of the terms. And what should be clear to you now is that the volume, the entropy, and the number of moles or number of particles are the variables of the internal energy. The other quantities, the partial differential quantities, are gradients. Hence, we write them as partial derivatives. They are essentially they're not variables, they are static parameters. So, you might go, what's the problem? What's the problem? Variables are the things we need to measure and control in order to get out the energy. Now, one can control volumes, and it can be done, but it's a little bit tricky. But what about entropy? Have anyone here ever heard of an entropy meter or controller? Because if you have, I would submit it to a journal, and you will be getting a Nobel Prize shortly after. Instead, let's be quite realistic. In our everyday fume hood, when we're doing reactions, when we're doing measurements, we can control the temperature, and most experiments are done at atmospheric pressure, or you can change pressure easily. So, volume and entropy are variables we don't want. We want pressure and temperature. We want to get all the information that the laws of thermodynamics give us, but we want it in terms of temperature and pressure. Which brings us to the need of a new thermodynamic potential. And what you can do is you can apply a technique called a Legendre transformation, and you can and that way create a new potential. And then what we call that new potential is the Gibbs free energy. And here it is written for you. G, the Gibbs free energy, is equal to the internal energy plus pressure times volume minus temperature times entropy. So, this is a rather odd equation. You might be thinking, well, this doesn't look like the thermodynamic identity that we've looked at. What's going on? But before we get there, a quick bio. Here is André-Marie Legendre. So this is a satirical sketch, watercolor sketch of him. Sort of crazy professor look. Quite a famous French mathematician, was born in 1752 and died in 1833. And the guy lived during some difficult times in France at the time of the French Revolution, Napoleon, and everything else around that. Don't envy him. Back to the Gibbs free energy. First law. Let's see whether the Gibbs free energy does what we need it to do. And we're going to check it by differentiating. So, just to be clear, we want to get something out that looks like the thermodynamic identity, but written in terms of pressure and temperature. Alright, there's our Gibbs free energy equation. We differentiate that, it becomes dg. It's equal to du. And now we apply the product rule, because we've got two different functions multiplied together, so we have to apply the product rule to separate the two entities out. So we get plus p dv plus v dp minus t ds minus s dt, which is what we expect for applying the product rule to the ts part of the equation. We now substitute the first law substitute in the first law thermodynamic identity. We know what du is equal to, don't we? It is equal to minus PTV plus TDS plus the summation of mu dn. We add the rest of the terms and we just eliminate. We eliminate PdV, we eliminate TDS, and our result is this equation. The change in the Gibbs free energy is equal to the volume times the change in pressure minus entropy times changes in the temperature plus summation over all chemical species I with chemical potential mu times the changes in the moles dn. Note, this equation looks very similar to the thermodynamic identity, the first law of thermodynamics, but it's been rewritten in terms of pressure and temperature as the variables. This result is also known as the fundamental equation of chemical thermodynamics. And it would be a good thing for you to know this equation off by heart. The Gibbs free energy is a function of pressure and temperature. See, if we just rewrite it in terms of partial differentials, you'll note that pressure and temperature explicitly comes out as the things that change the Gibbs free energy. And there's a very interesting consequence with this equation. If you think of the everyday chemistry experiments you have already done last year, they are done at constant pressure and room temperature, a constant temperature. So what's the change in pressure? The change in pressure is 0. dP equals 0. The same for temperature, dt equals 0. What you're left with is the change in the Gibbs free energy is equal to the sum of all changes in the chemical potential times the number of particles. Chemistry is about the chemical potential and changing amounts. This is why we are going to focus on the chemical potential on the course. And as you will see shortly in the next lecture, well, that Gibbs-Duhem equation that we derived is going to become really important so that we understand what this chemical potential variable is. And so the key concept I want you to take away from this lecture is the Gibbs free energy is a rewritten form of the first law of thermodynamics, but we do it in terms of pressure and temperature. Quiz question. The Helmholtz free energy is also a thermodynamic potential, like the Gibbs free energy, and is defined as F equals U minus Ts. Some textbooks will, instead of using F, they will use A. Either way, this is the equation. Given the definition of this Helmholtz free energy, what variable change has occurred from the internal energy? See you at the lecture.